Okay, 5 minutes at the hour, so we'll get started here. I want to thank everybody for joining. Got a few people on the WebEx this morning. So today we're going to talk about demystifying DAA, so planning for the distributed access network. What does it mean? What is DAA? There's a lot of questions, concerns. There's a lot of specs and things that are happening and a lot of movement in the industry. It's like we're at a tipping point in the industry where, you know, days of launching single channels of DOCSIS 1.0 and then 2.0 for voice and then 3.0 for bonded channels, now 3.1, just isn't enough. So the next phase of this industry seems to be moving down towards moving the equipment closer to the customers and calling that DAA. So my name is Mark Ridgeway. So I think I've met a fair amount of you. So I've been working with Mike Hartnett and at Casa Systems, and Mike and I have been supporting the shows. We do the shows every year, twice a year. We'll be out in LA. The next one, for picking fun spots to go to. So thanks to the NCTC folks, because they're always a good time. San Antonio being the last one, that was a good time. I've been at Casa for a few years now. I'm a senior solutions architect. You can tell by the fact that I have gray hair. As far as things are concerned, I would just say if you have questions, we do have the chat window, and you can just kind of pop a question into the chat, and when it gets to the end, I'll answer them all. You know, Mike and I and the rest of the Casa team are readily available if there's any other questions, and, you know, working with Melissa and Corey and the folks at the NCTC. So if there's anything you need from us, don't ever hesitate to ask. DAA, Distributed Access Architecture. Well, I always figure a good place to start are the specifications. You know, at Casa and myself, I'm a big fan of the specification because it gives you something to read at night. I'm not much of a fun person, so I read specifications. But the distributed access architecture, you know, when Cable Labs kind of thought through what they were going to do, they started creating spec. This 509. Last date was in May of 2018, so it's currently being modified and edited and enhanced, I would say. But the basis of the specification, it states that the modular head-end architecture, HAV2 remote PHY technology, it basically allows for the CMTS to support an IP-based digital HFC plant. So, you know, I've been in cable a long time. We used to think about the plant as the HFC. Seems like we want to push the ability to push packets further into the network in digital format versus analog, what DAA at the base of the technology provides. How that is accomplished in typical Cable Labs fashion, they allowed it over multiple solutions. They didn't lock you into Ethernet. So it's supported by both Ethernet, PON, GPON, or any other layer 2 technology. And this would run over the existing fiber, the existing layer 1 that you have in place. Kind of the basis of the solution from a definition standpoint. There is another DA architecture that people have been talking about is the MAC-PHY. So I'm going to focus on remote PHY. Remote MAC-PHY is a spec that's been out there. It was this last time this was updated was 2015. So I think typically the way it works is the spec becomes more in the forefront of analysis. You know, that's where the efforts and the focuses are. So I think remote PHY is sort of being pushed ahead of remote MAC-PHY. But remote MAC-PHY is still a viable solution, and there's good technologies behind that. Some discounted. If you break down DAA, the distributed access architecture, into the 3 components, what are the 3 base functions? We have the CCAP core, the RP, and the CIN. So the CCAP core is, you know, by rule or by definition, has to do everything that traditional CMTS does, except it has to add the ability to separate the MAC, the scheduling function of the DOCSIS communication protocol. It puts the scheduling function on CMTS, or within that, what's called the CCAP core. The RP, the remote PHY device, is the QAM upconvert. It's the physical upconvert. So the RPD has to have a layer 1 connection, connecting it to the core, and then a connection to the plant. So So the RP really takes packets in, IP connections in, and delivers up converts to the QAM of the service that you're deploying. Could it be a single carrier QAM for high-speed data, or a QAM for video, a broadcast or a narrowcast QAM, whatever it may be. That RP takes the IP physical connection in and does RF out. The third component is the SYN. So I don't know how they call it SYN because it makes me think of sinning, but anyway, maybe I'm it's Converged Interconnect Network, so the CIN. So in effect, so you have the core, you have the RPD, and what connects the two is the CIN. So that's really it. So you know when the spec was generated and the smart cable apps people were getting their heads together, they broke down into these basic components. A little bit of graphical representation of what that means. So in that hub or head-end site is where your core would be. So what I have pictured here is this is the Casa box. This is CMTS. Now CMTS is retrofitted with a CCAP services card, which would be the ability to take the MAC functionality and put it onto this card. And then I have a fiber optic, an SFP, a pluggable SFP, which leaves this card, and it traverses what's called this CIN. And other people like to call it fiber deep. This could be 10 gig Ethernet or 10 gig EPON. There's several options when it comes to this SYN, which I'll show you some samples. And then the RPD. And in this example, these are the Casa branded ones where we have our RPD, which goes in a typical node enclosure. So when we started thinking about taking our technology and deploying per this cable lab spec, this node has to meet the requirements for a node, right? It has to be able to be monitored, managed, line powered, wall power, whatever that may be. So these are really the three parts of what distributed access architectures are. This way I started looking at it was, how is it done today? I'm a big fan of how is it done today and really what's changing. So you're probably all familiar with this strategy, right? You have your CMTS, which has, downstream coax cable and an upstream coax cable, which gets input to an RF combiner, and those combiners feed this optical transmitter shelf, and the fiber leaves the building or the facility, and it terminates in your optical node with analog optics. The difference, or going to DAA, the main components are, the CMTS stays the same, and instead of using coax out, I use 10 gig Ethernet optics out of my CMTS. I put those into a switch. I have a piece of fiber, again, with these optics. These are 10 gig digital optics, and that terminates in the RPD node. A few options on how to do that. You can use a switch, or you can do a direct point-to-point. A lot of the folks we're in trials with are doing both. They want to figure out what's the best way to support this architecture within their environment. So they're doing a point-to-point as well, where I have that optic that lives within the CCAP core, and it traverses that fiber that shoots out into the neighborhood and terminates on that RPD node as well. So really what goes away is RF combining and the optical transmitter shelf. That's being replaced by the laser that lives now within the CMTS or in the CCAP core or within the Ethernet switch. And this is just all glass from this piece out to the node, and the laser terminates, or the optic terminates in the RPD node. So you no longer need to combine it or transmit it. So these pieces that go away. The things we talk about and give a little bit more in the presentation is typically other parts are brought in through your RF combiners. So you could have your narrowcast QAM or your broadcast QAM or other devices that transmit the QAM signals and managed kind of independently. One of the things you'll start to see or start to become more relevant or is now I can combine things on the IP side and deliver just, a glass with all of my spectrum contained within it, and that terminates on the RPD, and then it's up converted back to coax and delivered over the last 10 feet. Why, right? You always got to wonder why. So what we're starting to see, Mike and I have traveled around, and some of the other Casa folks, and been around the NCTC folks. What's going on out there? Why is this increased need for speed? Why is it when we launched CMTSs and cable, 8 meg throughput was enough, and now 1 gig is not enough? What's going on? So it's really, these patterns are accelerating the bandwidth demand, and the consumption model is changing. So we see, I have 2 kids at home. They don't watch TV. They're on YouTube. They're on Netflix, and they do all their stuff and interact with their friends over the IP connection. I still watch sports on my set-top and still DVR things and watch it that way, but it is shifting, and a lot of things as you're seeing, and you're starting to see this more of an emergence of over-the-top. Companies like HBO has an HBO Now, Netflix, Hulu, Amazon, all of these devices, starting to see some network convergence. So in most houses have wireless access points, and those wireless access points bring in any device that is within the range of your SSID or your radio that lives in your house. Bring them on. You're starting to see, 4K TV is becoming more relevant. I would say components drive technology. Well, 3 years ago when I wanted to buy that 4K TV, I think it was $5,000, and now they're $500. So they're becoming more readily available. So now operators are going to probably have to start delivering more 4K content. So again, these technology is shifting, patterns are shifting, and the consumption model is changing, and so bandwidth in the edge is increasing, which is driving the need to add more capacity, where DAA would be a good fit for that. There's this concept of the cellular Internet of Things. Got this statistic from somebody, and it said in 2014, people had 7 connected devices, and by 2020, they'll have 12. I look at this as, Amazon Alexa versus Siri, right? I have both, and I swear sometimes they talk to each other at night. But the reality is these devices that are coming to our houses and putting the cameras by our doors, now we can hit our doors with our, using these tools. This all consumes bandwidth, and I want to look at my door when I'm on business travel. I want to make sure, somebody's delivering a package, I can see them. That's all done over the internet. So again, technology accelerating bandwidth demand by these changing consumption models. I have this chart, which I liked as well, and we're starting to think of things a little different. So when you look at all these apps that are kind of appearing right now, home sensors, smart parking, video streaming, connected healthcare, you need to think about things maybe as from how much bandwidth does the application need, and how much latency will it work. So an example of the smart grid, it's low bandwidth, but it needs high it's very latency sensitive. Cloud assisted driving. I don't know about you, but I want that cloud to be able to connect to the internet so it doesn't go careening off the road. But we think about things in this sort of pattern. So as bandwidth increases, we need to be concerned with latency. So the evolving needs, the fundamental rethinking of the network. So really, this is all just sort of driving this increased requirement for bandwidth at the edge. The drivers that we're seeing, again, I kind of touched on them, but we're seeing an increase in the number of connected devices per person. Bandwidth is going up, right? 4K streaming, VOD over the top. I talk about there's also this demand for this complex interactive content. What does that mean? Well, if anybody has kids at home and they play Fortnite, they don't want to hear the kids yell at them because, they lost the game because their internet was slow. So I think parents are willing to pay that extra bit just to say, hey, go win it Fortnite, but then another time online. You're starting to see enterprises are outsourcing more. Amazon Web Services is a perfect example. Used to be they would house their DNS server in their own payroll department. Well, now you get the connection to Amazon, and you outsource all of that piece as well. Let the businesses focus on their businesses and let the network provide the functions. So enterprises are demanding more service as well. It's constrained by head ends and hubs and physical space limitations. Everybody's constrained by lowering CapEx and making sure OpEx is lower. We're seeing this continued plan. Folks are still doing node splits and splits. How that occurs. There's this concept called regrettable spend, which I'll touch on a little bit. At what point do it's kind of business as usual? How do I continue to grow my footprint, increase bandwidth at the edge? It's about maybe where direct DAA technology would help support that. Slide on benefits. So with the DAA strategy, so you see an OpEx cost saving. So that's reducing the power. So if I pull the electronics out of the master head end and put it out on the pole, I no longer have to cool that building anymore. So by pulling equipment out and moving it out to the edge with a PHY, which is the power-intensive component of HFC or of high-speed data, the PHY piece occurs. You're allowed that, lowering your OpEx by doing that. By pulling more equipment out of head end, you're also allowing you to start thinking about where equipment is located. So some stuff on virtualization, and one of the main benefits of virtualization is now I let the network sort of drive. If I have a data center on the east side of town, I put my things there, use my IP network to get out to the hub, and then my remote PHY to get out to the edge and to the consumer. I could sort of rethink where I put equipment and sort of put it in the places where it best suits my business needs. So one of the we're starting to see with this distributed access architecture is spec efficiency is improved. You know, by moving the PHY out to the pole, I get a higher MER within that node, which allows me to do some higher order modulation speeds. Now, most around 3.1, but you know, today 256K QAM is 3.1 or 3.0. You know, with 3.1, cable allows us to increase our modulation. So now I can go to 1K, 2K, and 4K, and the spec even calls out for a 16K. I can't imagine how many dots on a constellation pattern that is, but theoretically it's there. So in effect, I'm getting more throughput. We're seeing about a 50% increase in throughput by getting at higher order modulations by going from 256K QAM to say a 4K QAM. A couple other things: create a throughput, replace analog transport. It's all digital. So when I move the analog components, I'm alleviating the places where noise is introduced into my implant. I can sort of manage my noise floor a little better, extend fiber out to the home, tap into the existing coax, and launch some higher order modulation profiles. So we got OpEx savings, greater throughput and capacity, and then fiber efficiencies. So one of the things you start to see with going to digital is implementing technologies like DWDM, where I can have a five-starved part of my network where I use DWDM and maybe colors of light to go from point A to point B, peel those colors off through mux, and terminate them in my nodes. I can be more efficient with the way my fiber is. I don't have to consume a pair of fiber to do an up and a down. That's it on the benefits. So dive into trying to kind of demystify, or trying to sort of into a place where I can kind of understand it, which is what I always try to do. What we today is you have your existing head end, you have your telemetry systems, you have your broadcast, your narrowcast, your internet, your phone, and your CMTS. All this is kind of brought in, various technologies, whatever, bring you to this point. These all go to my RF combining the various pieces, my optical shelf, and out into my analog node. So if you're thinking that you have an area of your plant which is constantly being, 100% capacity, so you might need another node split, or you might have to address additional capacity out here at the edge. So you use your existing tools to sort of understand where the demand is within your existing footprint. So if you kind of look at it the way it's, or a segment of your plant, map it out today, see if you have some, military bases or a campus or some MDUs that are sucking down your bandwidth within your footprint today. The first thing you would do is you would upgrade your head end. So you could take your existing, I'll call it a legacy CMTS, and allow you to put in a CMTS that supports remote PHY. So the CMTS needs to be able to support the MAC, the MAC processing, right? The scheduling of the end users. So I upgrade my CMTS to support MAC processing, the scheduler. I might deploy a leaf switch. I don't have to, because there's a couple of options on that. But a leaf switch, which I'll get into that a little bit in the future, the thought behind the sign leaf architecture is it allows you to take the intelligence out of the switching architecture and just have it be a physical connection. So it's in packets out. Get a little bit more on that, but I take my head end, I retrofit or I upgrade my existing CMTS, I deploy some sort of optical termination link, and this all is online. I've got my existing combining my optical transmitter shelf, and I'm providing service out to my end solution here. The next thing I would do is I would deploy that DAA node. And so, for example, you know, the fiber might run through the same conduit, but in effect, I've got an optic here and an optic here. And this allows me to light this fiber with a 10 gig signal and terminate this within my RPD node. And so IP in, RF out. So the importance with the spec called out was now my ability to tap into that existing coax, so I can service all these users off this remote PHY node and tap into the existing coax to get out to my end subscribers. One of the things that's allowed, or per the spec, is I don't need to go, if it's DOCSIS compliant, that stays. If I have cascades and EDFAs and amplifiers, all that will stay. But what I'd be able to do is eliminate some equipment because I've now pushed I've pushed it from here out to here. Now I have 1.2 gigahertz of spectrum available with a launch power that might not need amplification out to some of these endpoints. The next we would do, well, so that's really it. So you upgrade your head end, you put your Mac or your Mac-enabled CMTS, you know, your leaf switch, which is your SIN, or your access technology. You deploy the node, you start mining it over, and then the next thing is you're allowed to start decommissioning all of it. The important thing here is these can run in parallel. So this is another segment of my network. I can leave that up and operational. What I do is I can deploy this DAA, this remote PHY node here, and start servicing people this way. And then eventually, as I continue down my plant, I decommission all of my existing RF combiners and optical transmitters. You know, the drivers, again, was to reduce cost and reduce space and reduce power. So by doing this, all of this equipment comes out of your master head end or your head end. So you can open that that remote PHY node, that node. Put it open here so you can see it. And this is our version of it. So if you're looking at other people's technology, I think relatively the same, but we're compliant with the spec. This is the way the fiber will come in through this port here, and this can be the 10 gig Ethernet, the SIN connection, or direct to the point. Terminate that optic within the RPD, which lives within the node, and then this takes all of the L2 tunnels that contain all of the connections back to your components. Those would be your high-speed data, your video, your QAM video, or your narrowcast that comes here, comes into the RPD. The RPD figures out what it is, and it sends up to the top of the node where it converts it to RF. Just routed from this source that sits here on the digital link into the RPD, which processes it, sets up the connection, then it takes that flow through the routers upstream and downstream out this RF connection. Now, once here, now it's standard coax, and you can start tapping in to the last mile or the last 10 feet into the home. And the other thing now is once you have this environment in place, now you can, this is 1.2 gigahertz capable. So now you can start thinking about, well, I can deploy 3.1, or I can put narrowcast QAMs on there, or I can really start to experiment with how to maximize my service within the environment that I've now created. And the other argument is this allows you to address the mid-split. So, you know, easier said than done. I know I left that up to people, and after about the first or fifth or sixth time of being told that that's impossible, you know, I fall back on, well, at the end of the day, if I've got this RF and this coax that provides my entry point from this pole or this node or this cabinet, I can use that existing coax versus the fiber to the home route. You know, trenching the yard, I'm not killing grandma's rose bush or whatever it may be, right? I'm not down that path. I'm tapping into the existing coax. And, you know, keeping this all digital allows this higher MER within the node, which allows me to start looking at higher order modulation profiles too, increasing my spectrum. So what we're seeing today is people are getting up to 5 gig of throughput off of this connector. So to me, it's a lot of high-speed data or a lot of bandwidth. fiber to the home really has a good competitor. And maybe if I want to look at full duplex or node plus zero, that this is a viable solution. Node. A couple other things, just again to try to sort of demystify. I've been around and doing this for a while, so we've kind of come up with some deployment considerations. So I kind of broke them down into these categories, right? And I talked a little bit about this Converged Interconnect network, the definition from K-Labs. I'm going to break it down into sort of a distribution and then an access as well. We start talking about deploying RPDs. We need to make sure that there's a straightforward way to provision them. I'll talk a little bit about spine leaf technology. I want to say go swap out all your routers because everybody has a significant investment with that. What I like to say is start thinking more with your router vendors to say, ask them about spine and leaf. If that makes sense to them, and where on that technology. At the end of the day, I'm a fan of it because you don't want to be restricted by your network devices. So deploying spine leaf technology allows you to kind of move away from being restricted and let the network and the application sort of drive the bandwidth. One that needs careful consideration is timing. There's a specific timing between the RPD and the CCAP core. A little bit on Netcom management. So the old days of Telnet SSH and SNMP kind of maybe hit its end. And people are considering technologies called Netcom and Yang. I'll show you a little about that. I've got some strategies on how to, again, how I go at this thing, right? How do I can't, are intimidated. They don't want to just start thinking about replacing nodes. That's a very complicated and time-consuming process. But there is a way to use DAA and deploy in a phased approach, which I'll show you, and a bit on virtualization. So on the interconnect options, so again, your Mac enabled, your Mac retrofitted, your Mac updated the CMTS now has optical ports on it, and these optical ports can be set, and all this stuff stays the same. You have your broadcast, your narrowcast, your internet, your PSTN, you've probably got a switch in there, you do AAA and subscriber management, you have your telemetry, mods and demods, all this stuff exists today. You take your existing CMTS, you update, you upgrade or enhance that CMTS to support the functionality, the scheduling functionality, and then you can use that port that lives on that and then haul your fiber over and then terminate that within that RPD node. And this is this is a straightforward point-to-point way of testing this. We've seen a lot of people go out, with their trials and do this. This part is, you guys know this stuff inside and out. Your distance limit, this is physics, right? It's distances, so the optics, as long as match, can go in and out, and as long as you meet your link budgets, and you're good to go. So you can deploy it like this in a point-to-point architecture. A little bit like I talked a little bit about the CN, this Converged Interconnect network, and Cable Labs put out there that says here's a way to do it. Here's options. Well, one of the options is you can deploy it over a passive DWDM solution. So if I'm fiber starved in between two of my network pieces, my hub maybe and some of the place exit points where I'm bringing in my nodes, I can use passive DWDM muxes. So I could have one port, launch with just a multimode optic, save some money, push it into a DWDM muxing capability or standard passive solution. I can call it color red, use my put this DM, I'll make it look like a wave, and then peel that color off and drop it in my node. I could do that same thing. Again, fiber efficiency is important, right? I can have another port come in as the color of green, bring it into my mux, use DWDM techniques to move that signal across the fiber, and then drop the green color in a different node. Matter, Phi here, using, might be constrained with fiber here, using DWDM optics and passive DWDM architectures. I can start doing this. And there's no reason why you can't have another one and another one and another one. So there's just, there's no limit. It's really limited by the physics of making sure that your fiber, your DWDM passives are, configured properly and you're managing your wavelengths appropriately. Another run into, people have said, well, I've got a network out there, and I'm connecting my hubs with MPLS or BGP or pseudo wires, or whatever they may be. So I've just pulled you on an example. We can use that exact same core. In this example, I can use this MPLS network that maybe just did IT connections or whatever between my hub sites, and I can build a tunnel. So I can take a color of that light into my thing here. In this sense, I could probably use multimode optics because I just have to worry about distance between here and my MPLS switch, MPLS-enabled switch. I build a tunnel across my core, and you can drop that color off on another set. So that's another way of using your existing infrastructure that you might have to maximize, extending IP reach using, from a cost, lowering your CapEx savings, using MPLS and an MPLS tunnel. This could be a pseudo wire. This could be, there's several other options in here that require, engineering around it. So one last one that they've run into some of the members out there that have gone down the path of deploying an active DWDM core. So this core exists today, and really all it is OEO. So it has optical, electrical, optical, and it has the ability to have low latency between any 2 points on this core. So I can do the same thing. I could come off of my MEC-enabled CMS, off of my optic. Again, this could just be a multimode optic because this distance isn't long. I bring this in as what we would consider in an active DWDM core as what's called an alien wavelength. Now I take that red color, I map it to here, and then I drop it here. So it's the same thing, and my lines don't quite line up. But now I've taken, so do point to point, real simple. Got maybe some nodes off of my head, my master head end. I can use passive DWDM optics in a fiber starved environment to use DWDM. I can use my network that I have there today, MPLS. I can build a tunnel, a pseudo wire over whatever else technology that I have from my routing environment, or tap right directly into my active DWDM core. In effect, keeping this as minimal impact as possible. This red, and at this point now, any site that has a drop on your core, you can deploy your nodes off. Those are some of the options when it comes to deploying what I'm calling the distribution CIN, this Converged Interconnect network. Again, Cable Labs came up with the specs. How to interpret them, read them, and deploy them is sort of to your nature. And I often think, like, if you're good with DWDM, well, this is a technology that could support it. If you have an MPLS network and you're good with that, you can use that as well. If you have an active core, you can use that as well. So it's kind of like take a step back, look at how you're connecting all your facilities, and then figure out the best way to maximize your existing investment while deploying this newer technology. Once I have those nodes, I have to provision them. So the things you'll find if you start reading through the spec, again, to demystify DAA, why there's the confusion sometimes around it. To provision a remote PHY node is basically the same way you provision a cable modem. So I bring up my cable modem, I come into my network, and then I get a DHCP address, gives the address, then I say, okay, is TFTP. This is where I set my .cm file, where I set its quality of service. I might have a firmware update to that cable modem, and then it does that, and then I say, okay, now it sets the time of day. So now I have timing, and my cable modem registers and it comes online. Well, both my nodes do it the same way. The same, Cable Labs, again, they made it simple. They kept the same process that you're used to. So, you plug in this node. The first it does is it goes and gets an IP address. So once IP address, it goes out and looks to where its config file may live, and there might be a firmware, just like a .cm file. It'll be a little different. It's what the remote PHY node does is it does cores now, and a core is really just a grouping of frequencies. So my grouping of frequencies could be, my 3.0 high-speed data. So it programs that, it does a firmware upgrade, and then it does syncs its timing. Once it completes all that node comes online and up and running. The thing is, when it comes to this RPD provisioning process, so, as you think about this, as you go down the path of having to deploy these, you're probably going to want to come up with some sort of workflow automation. So here's an example of how this field technician could go out, you know, you just do a phone. Most of the technicians are enabled with those. QVR, they take a picture of it, and then this RPD sends it over to this front-end app, and the Radius server authenticates that, says, oh yeah, you're a valid RPD, so it kind of checks that, and then it says, okay, get your address, here's your file update, here's synchronous on the timing, and then boom, you're online. So, you know, something to think about if you want to get on the path of deploying RPDs is take advantage of some of these automated tools that are out there. And I've kind of skipped through this. We'll make these slides available to folks, but you know, again, we want to like inundate people with new acronyms and whatnot or new technologies, but really what this is basically is the spine technology. And so the basis is it kind of goes away from the core aggregation access. You still have your core switches, but then there's spine and leaf. So there's a bunch of, you know, requests out here how to deliver this. You know, again, the real thing is keep the intelligence minimal on these things. You don't need to know every routing table on the internet on this switch. What you need to know is how to take packets in and forward them to the next upstream device. So spine leaf kind of plays into that fairly well. And when you think about spine leaf, and again, I was talking about it earlier, you're letting the network sort of dictate where your compute power goes. So spine leaf allows you to deploy it in a centralized model. I can have all my intelligence up here on my timing, and my core is all done up here and switching it out to my edges, or you do a distributed model. And that chart I showed you talked about, you know, latency and bandwidth requirements for various applications. If you think about that, if you're trying to deploy some, or they're trying to deploy some smart home applications, you might need to push a little compute power to the edge to be able to minimize latency. So again, spine leaf allows you to do that. There's no rules. I can push my compute power out to the edge here with this. That's kind of spine and leaf. Timing. I said now one of the requirements for remote PHY or DAA architecture is that timing is all synced. So some terminology, you know, they've selected 1588 V2. So it's just the Cable Labs recommending that. Some terminology now, you'll have the grandmaster clock, which is reference clock, and then you'll have your boundary clocks, and then your slave clocks, and however, how it manages all the timing. But one important aspect of it is, you know, cable itself is not asynchronous, right? So downstream is faster than the upstream. So they've built in tools within these, you know, turning off timing in the 1588 protocol to allow the lucky packet is one. And so it kind of, it's sort of always out here saying, how far is my clock? How far is my clock? It takes out all the network latency upstream and downstream, and it allows you to synchronize those clocks faster. And the requirement is that they must be synchronized. And there's a frequency of plus or minus a millisecond. So, you know, a lot of words there. At the end of the day, there are plenty of methods to make sure your clock, your grandmaster clock, which is introduced into your network, is shared amongst all network devices, including the RPDs. The other talked about, or I mentioned a little bit, is this concept of netconf and yang. When I first heard about yang, I didn't know what it meant, but it means yet another next generation. So I think whoever created that has a little humor in them. But in fact, netconf is really what it means, network configuration. And yang are the next generation or the next evolved SNMP, MIBs, or OIDs. So you all got SNMP out there in your networks, and you're all monitoring devices. And SNMP does a great job for that. But what we're seeing now, moving that Yang model allows you to kind of push the envelope a little bit and to start using these advanced tools, you know, better security and automation. And these Yang models, which can allow you to track more data from your devices and use it in a little bit more evolved state. So a simple way that I look at it is the way it's done today, CLI and SNMP. So you have your operator, and they're going to SSH, and I say telnet because, again, I'm gray-haired, I'm a senior engineer, is I SSH into each of the IP addresses on my devices, and then I type in commands like show running config or show cable modem, And if I need to configure a MAC domain or an interface, I'll actually type in the config commands at that point. And I'll type in here, I'll make my changes, and I'm good to go. I'll have SNMP loaded on both my cable modems and my CMTS, so I'm collecting all this stuff and sending it to a higher order server. What Netcom and Yang allows for you to do is now I can push my configs in a scripted way to a server or some device that lives within my network, and I can push those configs down to my server and let the server push all of them out to the CMTSs. I don't have to tell or SSH into each of them and type my commands. So, a good example is if there's some sort of DDoS attack happening and you need to put an access control list to block it, setting up and telnetting in creates an opportunity for manual intervention and problems. So this Netcom Yang model allows you to script that language, validate my configs, and then push them out. So I often think, it's 4 a.m. when I'm allowed to do my change run, I got to telnet to all my boxes. Well, in this scenario, if I pre-check all my configs and make sure everything works, at 4 a.m., I'm just hitting go. So it would be a nice place to be. Right, so I talked a little bit about the ability to phase this in. So as I was talking about earlier, you have your VOD qualms, and you have your broadcast qualms, you have your switch digital if you're running it, your legacy CMTS with your telemetry, all through your traditional RF, combining your transmitters into your nodes. So if I don't think about DAA, here's a way to do it. You're leaving all this stuff online and in production, and then you're introducing a MAC-enabled CCAP or a virtual solution, or taking your existing CMTS and upgrading it to support remote MAC-PHY or remote PHY. I can take that. I'm creating a SIN, which could be done, like I showed you, point-to-point over at DWDM, over an active core, whatever it may be, and I can target areas of my network where I have high demand or a lot of bandwidth being consumed. I don't need to upgrade my whole plant and redo my spectrum to add more channels. I can kind of come in piecemeal or strategically upgrade my network to solve those problems with this technology. Very compelling. Virtualization a little bit. Just again, sort of try to demystify, try to throw some stuff out there. And I mean, I have a real kind of a simplest look on things. But if you think about virtualization, what is it, right? So in the age, you would buy a server, and that server would have a hard drive, a processor, and power, right, or a network I/O card. So what they've done is just sort of group them together into this NFV, this Network Function Virtualization Infrastructure. But that's all it really is. I have a way to get packets on and off the network. I have to process those packets, and if needed, I need to put information into a database, and allows me to use the storage piece as well. So, and then there's several technologies or some solutions that are being evaluated. OpenStack being one, VMware, Docker, Kubernetes. People talk about VMs versus containers or bare metal. So this would be kind of your infrastructure layer with the network interfaces, the compute, and the node. And then how I take my VMS and then bring it in is done through an orchestrator, which is basically saying, okay, if I want to load a DHCP or I want to load a timing software, I say, okay, so what do I need? I need X amount of hard drive space, I need X amount of processors, and I need X amount of throughput. So the orchestrator builds this. And in effect, I don't have servers sitting there that are underutilized. They're configured and optimized to work within the exact requirements I need. We do virtualization of our CCAP architecture. So kind of built on this standard that's out there, we use the same approach where we can build our compute spine leaf, compute nodes, and we can take the application, the software application that we've written on our 700 today and migrate that over to a virtualized core. So why DAA, right? Everybody wants to know why, right? So got to be for things. So what we're seeing, and I kind of talked about it a little bit, we call it the spectral efficiency. So 25% improvement in end-of-line performance. So again, about 192 megahertz of a single carrier QAM, see about 1.5 gigabit of throughput. We're taking this to about almost 2 gigs of throughput. So you're increasing the bandwidth of a throughput, bits per hertz you're getting through that existing plant. With the codes and digital connections back to the head, now we can use these higher order modulation profiles. We can go from 256K to 1K, 2K, or 4K. The other thing you're starting to see, and I kind of touched on it on the SIN component, was now I'm just using pluggable optics. It's more of a commodity. I don't have purpose-built analog optics that I need to worry about and find and source and repair. I can go buy these pluggable optics and drive down the cost. Very simple, straightforward way to get the 10 gig connection from my Mac-enabled CMTS out to my RPD node. And these can be using standard DWDM, like I told you. Now, my distances with long-haul optics, I'm going past 100 kilometers. You know, it's the physics. The optics, as long as the optics has reach, I'm good to go. I can push out my devices, my RF, my upconvert to RF, further away from my hub and head end. I can eliminate my transmit and RF combining, like I showed you in the graphic, and I can take down, equipment within my hub and allow less cooling and heat and dissipation. We could use the argument that we feel that analog node splits, which is regrettable spend. We can think about instead of evaluating that in business as usual, maybe think about going to DAA, taking the cost of upgrading the CMTS to support the Mac functionality and putting the PHY out on the pole. That's the node split. Now you've gone to digital out the edge, and now you've tapped into that, increased your available spectrum to 1.2 gigahertz, theoretically, or raised the mid-split if needed, and you're really future-proofing the network. We feel like this technology is probably going to be good for a while. And I didn't really touch on remote PHY today, but there's, this concept of node plus zero, and then there's this other concept of full duplex. So down this path of, digital optics out to the edge, now I'm set up to take that RPD and upgrade that to full duplex. And then put all commercials against the fiber to the home you want, unless fiber to the home. So that's it. So I think I'm right about on time here. If anybody has any questions, I'll go into the chat window here, and you can type them in. That'd be when we get there and talk to people about DAA, what is the biggest concern from the operator? So, well, when I go out with Mr. Hartnett or whoever else, Tynan and the other folks from Casa on the team, the main question is how does this affect my existing work process around my plant sweeps, and how to monitor and maintain my spectrum, where pilot tones get inserted, how do I do that? So again, when Cable Labs created the spec, they put all that in there. So for anybody to deliver a RPD or a remote PHY-enabled node, you have to be able to plug into existing work processes. You have to be able to, provide carrier tones and pilot tones. One you are getting rid of is that analog link from that node all the way back to that end. So reducing the noise floor substantially, and being able to plug into existing tools that may be out there. Anybody else? I'm talking into a presentation. I usually do these with the open bridge so everybody can talk. Let's see, coming in here. So how do you compare fiber to the home versus DAA? So I look at it like, well, they both plays, right? And if the base tenet of the company is they're good construction and they feel like they're good at going in and trenching up yards and whatnot, and pulling that fiber, whether it's aerial or maybe it's conduits available. Greenfield makes a lot more sense, but going to the legacy environment and retrofitting and using that existing coax push that 5 component, that node, out to the edge, and tapping into that last 10 feet, last 100 feet of coax. In my opinion, now with higher modulation profiles, 1.2 gigahertz of spectrum, multiple FDM blocks, in about 4 gig, system 4 gig of throughput through that coax, that competes pretty heavily with fiber to the home. So, I don't know. I mean, I guess you'd probably have to look at it on a case-by-case basis, but I feel like, opinion, fiber to the home has a place. Casa has products that do PON as well, but this is really a seminar on how to take it. What is the most bang for your buck? How do I take my existing footprint, my existing coax, and deliver enhanced capabilities? That's it on the questions. So just want to make that, Casa and myself and Mike Hartnett and Tandem and some of the other folks from Casa have been out at the shows. We will be out there in LA at the Independent Show, booth 452. Come by and see it. We'll have our remote PHY node there. We'll have our C40, our CSC card, show you, your hands on it, see it. We have it up and operational, showing you the 4 gig of throughput. How to step it up, right? Step up your broadband network potential. How do we take example, or how do we take advantage of our existing footprint, maximize our existing investments, and deliver the next generation solutions? And I think that's it. If you have any questions, you know how to get a hold of anybody on the Casa side. You can, pop an email or give us a call or stop by the booth, and we're here to help. If you have questions, my name is Mark Ridgeway at mark.ridgeway@casasystems.com. Pop me out. I think I've met most of the people, been at all shows, and have traveled to the members' sites. Some of the highs are Hayes, Kansas, and we see GCI up in Alaska. So, we're to come out there and sit down and sort of look at networks and look at your existing strategies and your business plan and position some architectures and some solutions that are going to help you meet your business goals. And with that, I'll stop the recording. And I appreciate everybody's time today. And hopefully we'll see you out in LA at the show. All right, thank you.